So good morning. It is Thursday, October 29th, 2020. We're going to be working with what's called the standard normal distribution today and using table A. We'll do some examples so that you can see how to use this new thing. Today isn't a whole lot of new information necessarily. It's just some new tools that we can use to help answer questions. Right. So first, we're going to talk about the standard normal distribution. This is based on what we have seen already with normal distributions and the 68, 95, 99.7 rule. All right. It's clear that normal distributions share many characteristics. Right. They are all unimodal, symmetric, and bell-shaped. No worries either. And can be completely described with the new notation that we learned about with n parentheses mu comma sigma. Right? If we have that, we know what the standard deviation is, we know what the mean is, we can draw a rough sketch of the distribution. All right. All normal distributions are the same if we measure in units of size sigma from the mean mu as center. Right. To do this, we must standardize the distributions using the z-scores. This is why we've looked at standardized scores or z-scores. We use that formula z equals x minus mu, or x minus the mean, divided by sigma, which is our standard deviation. Okay. If the variable we standardize has a normal distribution, so does the new variable z. So if I standardize all of the observations from a normal distribution, that new set of data, that's all the values of z for every data point, is also a normal distribution. Right? This new distribution with mean mu equals 0 and standard deviation sigma equals 1 is called the standard normal distribution. And that's what our standardizing does. It makes it so that mu becomes 0 of that set of data, and then everything is kind of measured with a standard deviation of 1. All right. This is kind of like our lead up to the formal definition for the standard normal distribution. Does anyone need a moment to write anything down from this screen? Please raise your hand. Excellent, I shall wait. All right. Next. Here is our formal definition from the textbook of the standard normal distribution. Standard normal distribution is the normal distribution with mean 0 and standard deviation of 1. That's what we see in this picture here. Right. We go from 3 deviations to the left to 3 deviations to the right, and we have our curve. If a variable x has any normal distribution n mu sigma with mean mu and standard deviation sigma, then the standardized variable z equals x minus mu divided by sigma has the standard normal distribution n, 0, 1. Right? The picture up here is essentially a sketch or a picture of the normal distribution n, 0, 1. Right? The center of this distribution is at 0, the mean is at 0, and the standard deviation is 1. Right. Any questions on this definition? Right. Can you raise your hand if you're writing this down and need time to write? All right. So the standard normal distribution, just like any other normal distribution, the 68, 95, 99.7 rule applies to the standard normal distribution. That is, 68% of the observations lie between z equals -1 and z equals 1, within one standard deviation of the mean mu. What happens if I want to know the percent of observations that lie between z equals -1.25 and z equals 1.25? Right. I no longer can use 68, 95, 99.7 rule because that only uses standard deviations of 1, 2, and 3 away from the mean. Right. So that means we need to use the standard normal table known as table A. Okay. You will have access to this table when you take the it will be in the notes that are the formulas and tables and things that are provided to you. You do not need to memorize this. That would be absurd. This table works because all normal distributions are the same when we standardize, and table A provides the area under the curve for this standard normal distribution. We're going to take a look at table A, which I have here. Excuse me. All right. Now this table A is the same table. Let me zoom this out just a touch. There we go. That is provided in the formulas for the AP exam. Copy of the formula sheet and tables that were provided for the 2020 exam. Right, so you'll be provided this. The first table you get to is table A. It's a lot of numbers and a lot of values, and I'll show you how to use this. For now, essentially, if you're looking for a z-score somewhere along our horizontal axis, table A will give you the probability or proportion of observations that are less than z, or less than that z-score. Okay, so let's look at an example. All right, we have our standard normal table. Table A is a table of areas under the standard normal curve. The table entry for each value z is the area under the curve to the left of z, which is what I was just describing using the picture. All right, for example, suppose we wanted to find the proportion of observations from the standard normal distribution that are less than 0.81. Right, we have 0.81 right here on this graph. And right, to find the area to the left of z equals 0.81, we need to locate 0.8 on the left-hand column of table A. Okay, so this is a portion of table A that's been provided here. We find 0.8 here. Then locate the remaining digit 1 as at 0.01. Right, when I put these two together, 0.8, 0.01, I get 0.81. The entry opposite 0.8 and under 0.01 is 0.7910. This is the area we seek. All right. So this number here at the intersection of those two values, 0.7910, this is the proportion of the observations less than 0.81. We also see this in the picture here. We found 0.81. The value from table A tells me the proportion. That's the shaded area. Right? So essentially 79.1% of the observations are less than 0.81 standard deviations. Right? So that's kind of how we use this. Any questions? we're going to look at some examples after this, but are there any questions so far? Anything I can clarify? Does anyone need another moment to write anything down from this slide? Right. So let's look at an example. What proportion of observations are less than negative 0.53? Right, so got a copy of our standard normal distribution here, and I've marked here where approximately where negative 0.53 is. Right, so we're 0.53 standard deviations to the left or less than the mean, and the proportion of observations that are less than that is essentially I'm looking for the shaded area right over here. Looking for everything over there. So what I do is I've pulled a portion of our table A here into the screen. I'm looking for 0.5 first under Z, negative 0.5, I get that here. And then I'm looking for 0.03 in this column here, in this row. And then I find the intersection of those two things using the table. So I'm going to go down from here. Look at this row. Right? And so that means the number I want is 0.2981. Right? So that means that the proportion of observations less than negative 0.53 is 0.2981 or 29.81%. Right, so that's how I can use table A to find the proportion of observations is essentially the area under the curve where the area total is 1, right? We have 0.2981. Right. Is there any questions so far? Anything I can clarify or make more sense of? All right. Next example. All right. This one, I'm going to make a slight change to what I typed here because I made this early this morning and I made a mistake. We're going to have this be 1.25. I did not include enough of the table to do 8. So we'll do 1.25 here. Sorry about that. That way I can use my table. All right, so now I want to know what proportion of observations are less than 1.25. So again, I'm looking at the area under the curve. Right, that is all this to the left of Z equals 1.25. And all this area here, I want to know what proportion that is. So again, I'm going to start by finding essentially the root of this number is 1.2 in the left-hand column with Z. And I'm going to find 0.05 in the row across the top. And then I find the intersection of those two things, and that's going to be this number here, 0.8944. So again, that tells me that the proportion of observations less than 1.25 is 0.8944. Again, we could say that as a percentage as 89.44% if we wanted to. Okay. All right. What do you guys need explained better? What does not make sense so far? We're doing okay. Okay. So we need another moment on this slide. All right. All right, in this next example, once again, we're going to adjust this number to make it work with my table. This to be 1.25. All right. We want to know what proportion of observations are greater than. Right. So instead of to the left of this number, which is the value that table A will give me, I want to know what proportion is to the right. That would show the greater than portion. So we already know, right, we have 1.2, 0.05, and that lands on my table, 0.8944. But that's the portion less than 1.25. I need the portion greater than. Remember that the area under the curve equals 1 as a total. So the part to the right plus the part to the left, 1. Right? So that means that the 0.8944 plus the proportion of observation greater than, right, 1.25, which we don't know, right, that's some value, call x, needs to equal 1. So we subtract, right, the 0.8944 from 1 to find out the proportion that is greater than 1.25. And that gives us 0.1056. And we can answer the question, the proportion of of observations. I'm going to use some notation here. Greater than 1.25 is 0.1056. Okay. So we're using the table, but not just taking the value this time. We have to subtract that from 1 to get the greater than amount. Right. Any questions on this part, on this example? Okay. Next, we want to know what proportion of observations are between. Right, now we're in between two numbers, negative 0.53 and 1.25. Okay. So we already know from our previous examples, right? We have the negative 0.53 value here. And then we have the 1.25 value here. And again, I've only taken portions of table A so that we can see the numbers that I wanted. Obviously, we've seen the table itself is a little bit longer than this, considerably longer. All right. So I have these two values now. How can I use them? So if we look at the table, we know that the proportion of values less than negative 0.53 is at 0.2981. We also know that the proportion of values less than 1.25 is 0.8944. So that leaves us with wanting to know, essentially, what's the difference? So you go from here to here. What is that number? Right? So we can do the algebra essentially, right? We can say, okay, well, 0.2981 plus whatever x is needs to equal 0.8944, right? So the value of x, which is the area between these two spots, is a 0.8944 minus 0.2981. Which again, we'll go to our trusty calculator. We get 0.5963. And so we have the proportion of observations between negative 0.53 and 1.25 is 0.5963. Right, which again we could say is a percentage of 59.63% of the observations lie between negative 0.53 standard deviations and 1.25 standard deviations of the mean. Okay. What questions do you have? What can I make more sense of for you? Got one more example. In this example, I want to know what is the value of z right here. It's this red line on my distribution, right? The area to the left of z is 0.8. So 80% of my observations are to the left of this point z, right? So that's my proportion here. Okay, this is going to be 80% of my observations are to the left of here. All right. So we have to work backwards to find z. We're going to have to kind of construct z out of the information we know. Right. So what we do is we use this 0.8 as our guide, and we need to find within our table, we're going to find the proportion closest to this number. All right. So in our table here, we're just going to look for 0.8. We're as close as we can get. And it's obviously not in this top part. It's going to be closer to this bottom section here. The last row is a little too high, right at 0.81. We have 0.8023, and we have 0.7995. These are the two closest numbers to 0.8. We want to go with whichever one is the closest, like numerically closest, right? 0.8023 is 0.0023 greater than 0.8. And then 0.7995 is 0.0005 less than 0.8. So numerically, this is closer. So that's the value we're going to use as like in the table. That's as close as we can get. We cannot get any closer approximations. These are the only values we have to work with. So from this value, we're going to follow it back over to the left. To the decimal that it corresponds with in the first column, the z column. And we'll go up to find the second decimal place that it corresponds with in the z row. Right, so we have z here at the top left corner. So we put these two things together and we get 0.84, which is the value of z. So we've kind of worked backwards, starting with the value that's on the table, and then constructing the z-score from there. Could then, if needed, convert the z-score back into the units of measure from the original distribution if needed, by just working backwards through the z-score calculation, but we're not doing that today. Alrighty. What questions do you guys have? That was the last example. What can I clarify? What can I make more sense of? What can I explain better?
Can you explain why it's 0.84 instead of 0.85?
Okay, why did I choose the 0.7995 and not 0.8023?
Yeah.
So again, I need to find the number that is closest to the one that I've been asked for, which is 0.8, right? From 0.7995 to get to 0.8, I have to add 0.0005, right? So we have 0.8 minus this 0.7995 equals 0.0005. right? I'm only off by 0.0005. For this other value, right, we have the 0.8023 minus 0.8. That's going to equal 0.0023. And I'm doing this because I just need to know how far away is each number from 0.8, because I need to choose the one that's the closest, right? In this situation, right, using the numbers that I have on the table, the 0.005 is a shorter distance to get to 0.8. So this is closer. So I use that value in the table instead of the 0.8023. They're both very close. And 0.8023 has 0.8 in it, but it is technically farther away from the value I'm looking for. So I go with the one that's distance-wise closer.
Oh, okay, thank you.
You're welcome. What else can I clarify? How else can I help? Okay, so then let's go back here. So then, if we look at our discussion board for today, there already is some answers. All right, so you're going to be using table A, which I have linked right here. You can click on here to download the formula sheet and tables, or you can just open it up in the browser, use the little magnifying glass guy, to find the proportion of observations from standard normal distribution that fall in each of the following regions. So you're going to do where there's a z-score less than 1.39. So what proportion of observations are less than 1.39? What proportion of observations are greater than negative 2.15? And what proportion of observations are greater than negative 0.56 but less than 1.81? That's the first three. So in the first three, you're just figuring out these values using table A and a little bit of arithmetic. The second part here, you're going to use table A to find the value Z from the standard normal distribution that satisfies each of the following conditions. In each case, sketch a standard normal curve with your value of Z marked on the axis. Okay, so this is like the last example we did. So on number 4, you're finding Z marks the 20th percentile. So essentially, remember with percentiles, that would be 0.2 as a decimal. And the 20th percentile is where 20% of the data is less than that, or 20% of the observations are less than. So you're attempting to find the z-score that corresponds with a value of 0.2 on your table A. On question number 5, it's looking for the place where 45% of all observations are greater than z, which means you're looking for the z-score that corresponds with a proportion on table A of 0.55, not 0.45. 0.45 is for greater than, which means 55% of the observations are less than, and less than are the values that you find on table A. Okay, so this last one is worded a little, not necessarily tricky, but you need to read it carefully.